A student, whether you are a student at Purdue, Findlay, Taylor, Valpo, IU, or any of the other universities who have students here, hold your hands up. People who are looking to hire students. There they are. Yeah, some of them are now waving a little more vigorously. All right, on students as well. If you're a Taylor University student, your professor, Professor Stanley, wanted me to remind you that he has eyes in the room. Don't embarrass him. He didn't really say that, but Danny's a friend, so I thought I'd throw that out. With that, we'd like to move along to our next point on our agenda, which is our first panel discussion of the day. So security through formal methods and secure architectures. The idea for this panel came up that two things. Raytheon reached out to us and said they were holding an internal technology summit and wanted to know if we had anybody working in the area. A few years earlier, one of our partners at the time, Rockwell Collins, had said, boy, you guys should be doing more in this area of formal methods and secure architectures because we're really interested in this. We looked around and we were doing a little bit, but it hadn't caught on. Well, when Raytheon called just this last year and started doing it, I said, you know, I know we have a few people that are doing some really cool stuff, but it took the opportunity for me to blast out to our faculty and say, hey, if you guys think that something that's relevant in this space, let me know. And I was bombarded by our faculty. Many of them new faculty had joined CERIAS and come to Purdue in just the last 2-3 years, who are doing some unbelievably really cool things. And I said, okay, we need to highlight what we're doing. Because this is an emerging area for ourselves, but also is in an area of growing interest within the industry. And as Spafford said, it had its highlight, it kind of went away, and now people are realizing there's some lessons to be learned from formal methods as well. So I'm excited to be an audience member for this. We do have one disappointment. Unfortunately, we've all seen on the television the last couple of days that travel schedules and the airlines are going through some difficulties right now. So one of our panelists was not able to join us today, but that will mean that we will be able to give each one of our panelists an extra 30 seconds to present your thoughts before we take Q&A. So with that, I'd like to bring up our panel moderator, who is one of these Purdue faculty members who is working in this area, a CERIAS fellow, a longtime faculty member and great friend, and one of our technology leaders within CERIAS faculty, Professor Saurabh Bagchi. Saurabh?
Good morning to you all. My name is Saurabh Bagchi. I'm the moderator for this panel, which is going to look at how do you use formal methods and secure architecture in the field of security. We have 3 panelists with us, Ben Delaware, Rupsha Shamanto, and Matt Wilding. Ben and Rupsha are from Purdue University, and Matt is from Rockwell Collins. So I'll give a short bio for each of our panelists, and then kick off with some opening remarks. So Ben received his PhD in computer science from UT Austin, working with Professor William Cook. He then worked as a research scientist in the Programming Languages and Verification Group at MIT until fall 2016, when we were very happy to have him join us here as an assistant professor. His research is on the design and implementation of programming languages and tools that provide higher assurance and lower effort through the use of mechanized theorem provers. Rupsha is also an assistant professor here at Purdue. Her research focuses on building reliable and efficient programs using formal methods and programming language principles. And her work has had applications in a wide variety of domains, including concurrent system software, probabilistic and cyber-physical systems, and educational technology for programming courses. She also did her PhD from UT Austin, working with Alan Emerson and Vijay Garg. And then from 2014 to 2016, she was a postdoctoral researcher at the Institute of Science and Technology in Vienna, Austria. Dr. Matt Wilding is a principal research group manager in the Rockwell Collins Advanced Technology Center. He received his PhD in computer science, also from UT Austin. For full disclosure, I did not receive my PhD from UT Austin. And he joined Rockwell Collins in 1996. He has worked on many high confidence efforts such as the machine checked formal method analysis of the AAMP7 microprocessor, which has been critical to lots of Rockwell Collins products. He currently leads the Trusted Systems Research Group, which collaborates with various product groups within Rockwell Collins. So let me start off by giving you some of my thoughts. I'm not an expert in the area of formal methods, so I would love to hear our experts knock down some of the straw men I have for the use of formal methods. So basically, formal methods to me enables that you can reason from logical or mathematical specifications of the behaviors of computing devices or processes. And if you use it right, you would be able to provide a rigorous proof for that the system behavior will meet some desirable property. For example, your program does not crash when you pass it this set of inputs, or your program terminates under these kinds of environmental conditions. There are lots of exemplars where formal methods have found use. For example, you could think of contemporary cryptography relying on formal methods in a broad sense of the term. Synthesis of secure programs, as well as these correct by construction methods, for example, zero-knowledge proofs, also use formal methods. And the area has developed a mature set of tools and has found wide application in various domains, such as verification of hardware, verification of embedded systems, and testing of software. And what about secure architecture? Just like when we start to construct a building, we don't just go off and start pouring concrete. We start off by creating a blueprint. So in a very simplistic view of the world, you could think of your system. First of all, you sit down and define an architecture for your system. Then you come up with the detailed design for your system, leading on to the implementation, followed by testing and verification. So the architecture lets you make explicit what are the security goals of your system. What is the adversary model that your system is supposed to be able to tolerate? And it also importantly illuminates the dependencies that your system or infrastructure has on other infrastructures. For example, what are the trust relationships between the various principles you have in your system? Or what are the trust relationships between the various subsystems that you have that you're relying on? What are the control and data flows that can go across infrastructures? And even on the personal side of things, how would you allocate personnel for different subsystems in your overall system? Sitting down and thinking about the architecture of your system hopefully lets you make these kinds of decisions. So I have one slide on why you would want to use them for security, and then one slide on why you would absolutely want to run away from them if you want to build secure systems. And it's in the second one that I would love to hear from our panelists how to break down those straw men. So in terms of formal methods, to me, they give you the hope that you could break out of this perennial cat and mouse game between the adversaries and the defenders, where the adversaries come up with a new kind of attack technique, you build in a new kind of a defense technique, and this game goes on. And on the side of privacy, when we talk about privacy guarantees, too often we think of it as a very fuzzy kind of a concept. But when you say the word guarantee, it really should mean that, guarantees. And formal methods, if they're properly applied, could help you get toward these kinds of guarantees. And there have been a very rich set of verification tools that have been developed, that are being developed. So I think the field is coming to a point, or has already come to a point, where it can be applied on real systems. In terms of the secure architecture, I think there are certain fairly solid reasons for why you would want to use them in building reliable or secure systems. It brings the necessary rigor to your design process. So you don't just start off by pouring concrete. Rather, you start off by laying down what are the design principles that your design and then your implementation needs to follow. It can importantly help align the business processes with the security processes, which is oftentimes a problem in the security world, where you can come up with the best techniques in the world. If it's not adopted within your enterprise, you don't get very far. And it can be a pathway to the application of formal methods. So these are my high-level thoughts about why you would want to use them for security. And here are the reasons why you should absolutely run away from them if you want to build secure systems. And these are straw men. These are easy criticisms to level against formal methods, that it needs too much expertise. You need a PhD, and a long PhD at that, to be able to apply formal methods. the tools often are not mature enough. They work when you apply them at small scales, but they break when you apply at large scales. They give you too many false positives. They cannot handle dynamic data sources. So these are all the reasons why you really cannot apply them to real systems. And probably the single most important factor is it lengthens your development time. So it postpones when you can ship your product. In the case of secure architecture, it needs several people to sit down and talk. And engineers never want to sit down and talk, especially when the payoffs are very far off into the future. Why would we agree on a secure architecture when we won't actually see the payoff for 5, 10 years down the line? It needs too much expertise. Again, the security groups may not always have expertise in building secure architectures, and it lengthens the development time. Again, the same argument for not using formal methods. With that, I will stop. And I will let our panelists go. Ben Delaware would be the first one who would start off. And then we'll have, after all the panelists are done with their opening statements, we will have hopefully an interesting Q&A and discussion session.
I'm giving away the slides. OK, there we go. OK, right. So the prompt was, what is holding adoption of formal methods back in industry? And I think the answer there was alluded to is the standard argument that the cost of deploying the formal methods to verify our software outweighs the benefit, or at least this has sort of been the prevailing wisdom for years now. And so I would argue that the benefits of formal methods are pretty clear, and I'm going to draw an analogy here that if you go out to build a boat, right, the promise of formal methods is that we can formally show that this boat is not going to have any leaks in it before we throw it in the water. So the common paradigm right now is, maybe you have a blueprint for your boat, and you throw some people at it, but you don't have time to put it in the water. You don't have a proper testing, pool to test it in. So you get a hose out, and you send some, unlucky interns to sort of spray some water on the outside of the hole, and hopefully you'll find some leaks along the way. You'll patch them up. You'll say good enough, and you'll throw it in the water, and hope the boat doesn't sink. And if you discover any holes along the way when the boat's out to sea, well, you'll patch and pray is the standard approach. And what the promise of formal methods is, or the promised benefit, is that, no, we can verify once and for all with mathematical certainty that you put this boat in the water and it will not have any holes. You've completely reduced the attack surface to someone shooting a torpedo at it, for example. OK, so this is the benefit. High assurance software. Of course, the costs are pretty clear, too, as was also alluded to in the introduction. Or at least the perceived costs are clear. So the first of these, of course, is that not every boat is worth verifying, right? There is a lot of effort involved in developing proofs for these systems, and patching is cheap. So if we have a toy boat and we're going to deploy it in the tub, who cares if it springs a leak? You can have the parent patch it up, hopefully. The kid might happily just pull it out of the water, dump it out, hopefully not on the floor, and then keep playing with it, right? So are formal methods really worth the effort? The other one is just terms of scale, right? There have been a lot of concerns about how these methods scale to realistic systems. And so you're either forced with reasoning about, say, toy programs, or you model the program, some sort of blurry approximation of what you actually want to formally verify and show as secure. And now you have a gap between the model that you have and the software you deploy. And this gap, of course, is a convenient attack vector for people. So there's a real question of how we scale formal methods to what we actually want to verify or guarantee is correct. And then finally, again, this is one of the big ones, you need arguably some degree of expertise to use these systems, right? You need a PhD in computer science, apparently from UT Austin, in order to work with these systems. OK, so I would say that this perception of costs, well, realistic is the costs are not as clear as I've just laid them out. They were clear, but there are mitigating factors that have come into play in the past, say, 5, 10 years. So on the effort, of course, who cares if your web app crashes, right? That's OK. We can reboot it. But what happens if your car crashes, right? That's a little bit more dangerous. And patching the bug is not going to put the genie back in the bottle once the bugs are out in the wild. Additionally, even for toy programs, if the web app is connected to other subsystems and say the Internet of Things, to throw out a buzzword, well, we can hack this easily, this web app, and have it start sending carefully crafted malicious packets that can bring down your entire house, right? I suspect it's only a matter of time until we see someone, put someone out of house and home by turning on their Nest and blast air conditioning all the time or something like that. So even seemingly trivial applications or software, it now becomes important to make sure they're secure in some sense, so they can't affect other components. Of course, the other issue is scale, as alluded to before. We've got this formalism gap, and the good news there is that we really can verify realistic programs now. Thanks to the power of Moore's law, we have more powerful reasoning systems that can scale to very large programs. We've developed mature technologies that can reason about programs down to the last byte. We can actually verify formally the code that we are deploying on the machine. And we can verify the machines themselves so that we can have a proof that the code that actually gets executed does exactly what we wanted. And there have been several really powerful examples of realistic systems that have been verified using formal methods and machine-checked proof. There's the CompCert verified compiler, which is a real C compiler that produces a proof that the code that you stick on the code that you output behaves exactly like the code that you put in at the beginning. That is, the compiler doesn't introduce any semantic errors. There's the SEL4 verified microkernel, where we have strong guarantees about isolation between the components. And Microsoft is developing a verified HTTPS stack using formal methods called Project Everest. And there are many other examples out there. So we have shown that we can now scale these to realistic systems. And of course, the expertise question is easy. We just need more people to come to grad school. So you need a PhD in computer science. We'll get a PhD in computer science. Well, maybe not. I think the argument here is that now we've developed these technologies that are mature enough that we can actually stand on the shoulders of giants, right? If you don't need to be an expert in formal methods to use a certified compiler, but you get the guarantees about the code it produces. Similarly, if you want strong proofs about isolation in your embedded system, you can use this verified microkernel, and you get a stronger security guarantee. And on top of that, as I said before, people in the in the PhD or just in grad school or in academia are actively working to develop better tools that you can use at lower cost. There's a lot of work in synthesis where we are developing systems where you can just write down the specification, and now the system will produce a program with a proof that it's correct. So we're lowering the cost of entry to the system is getting lower and lower to the point where you can just use sort of off-the-shelf technologies, sign off and say formal methods inside, and you have a stronger, more secure system. So those are my straw men. I've knocked them down. I'm waiting for some better attacks during the panel discussion. So as I noted, what did I say was holding formal methods adoption back? Well, I think that there's this perception that the costs outweigh the benefits, and the scale is slowly tilting the other way, where the benefits of these systems are starting to outweigh the cost. Thank you.
Okay, so I'm very happy to hear Ben's talk because it gives great introduction to what I'm going to say. I have pretty much the same points to make, except I'll probably use a little bit more detail based on what he introduced. So I have taken the liberty to interpret the title of the panel a bit more liberally. I'm just going to talk about formal methods and security. I'm not an expert in security, but I am an expert in formal methods, and I want to tell you a little bit more about what formal methods mean, what they are able to achieve today, and what I think the community agrees on the challenges that industrial deployment of formal methods for security applications entail. So let's start with the bird's eye view. So this is essentially what Ben was talking about with his ship and boat example. So this is what is typically done for ensuring software reliability across the board in many industries. So this is essentially the testing approach. So developers would write a program, and then either the developer or due to ancient wisdom, there would be some informal specification of what the program is supposed to do, or some set of test cases which are used then to check if the program is correct. So there is this testing phase where, starting with a software program and some informal knowledge of what the program is supposed to do, there is a process of checking if the program is correct. So you just run the program using your test inputs and check if the outputs are what you expect them to be. So well, if these tests, if your program passes these tests, then you just declare the program to be correct, okay? And if these tests fail, then you start an iterative loop of basically debugging and repairing the program until you are satisfied with what the testing phase gives you. So until your program has passed all the tests, for instance, and then you declare the program to be correct. So this is the testing approach, and there is a famous quote by a famous person that some of you might have heard of, who also spent time at UT Austin. So Dijkstra said, I identified very appropriately that program testing can be quite effective for showing the presence of bugs, but is hopelessly inadequate for showing their absence. Okay, so if you are interested in verifying or guaranteeing that a program is correct, this testing approach is not going to help you provide such guarantees. Okay, because when you have declared this program to be correct, it is correct according to your set of test cases or some informal specification. And that is not a formal notion of correctness. So what a typical development cycle that is enhanced with the use of formal methods is going to look like this. So you again start with a program, and instead of having an informal specification or test cases, you formally articulate what the specification of your program should be using some mathematical logic. Okay, so think of this as a very precise and mathematical description of what your software or what your system is supposed to do. And then instead of testing, you employ formal verification techniques to check if your program satisfies the specification. Okay, so what we have, I mean, I'm not going into detail here, but what we have done with these changes is essentially introduce a lot of mathematics-based precision into specifying the system property, and as well to checking if the system satisfies the property. And then in more recent years, these parts of the program development cycle, which are done by programmers or by human developers themselves, are also being replaced with automated techniques. So this whole loop ends up being automated, because a human programmer can make mistakes, and similarly a human debugger may also make mistakes. So in fixing a particular error, a human debugger may introduce more errors. So formalizing and automating these parts of the development cycle are also crucial in ensuring program correctness. So now when you have gone through this iterative development cycle and the program verification engine says that your program is correct, you can indeed declare that the program is correct. Okay. So let me just mention one caveat. I think Saurabh and Ben both mentioned this thing about 100% guarantees of system correctness. Okay, I just want to clarify that there is no such thing as a 100% guarantee of system correctness. So we are going to, this is going to help us build software and systems that is far more correct or far more secure than what traditional testing based human-driven approaches can, but there is no such thing as a 100% guarantee. That's because somebody has to come up with this formal specification. Somebody has to implement this verification engine, and there can be incompleteness and errors at all of these stages of the verification process. So that's an enhancement of the typical program development cycle with formal methods. Here is another approach that one can take to develop correct programs. So this is the program synthesis or the program completion paradigm, where I'm just showing you one instantiation of this paradigm, where you can have a programmer just write a partial program, leaving out a lot of the trickier details of writing the program. And then you feed a synthesis engine, this partial program, and a formal specification. And the synthesis engine automatically generates a program that is correct by completion or correct by construction. Okay, so this is the promise of program synthesis, where you eliminate this iterative cycle of checking if a program is correct, then debugging and repairing, and then doing it again. Instead, you just have a programmer write what the programmer can write best. So this partial program can capture the best human intuition that a programmer can bring in, whereas the synthesis engine can take care of the tricky, dirty details that humans usually fail at. And together we can have a program that is correct and, in our context, secure. So that was a bird's eye view of formal methods in general. And here's just some terminology that I'm going to throw at you so you have something to talk about after this panel. So these are the three different classes of formal methods, broadly speaking. There is a deductive verification based on theorem proving, and Ben talked about some of this. There is also model checking and abstract interpretation or static analysis. And some of these methods are more automated than others. Some of them are more, they can handle more, or let's say they're just more expressive than others. So I'll come back to this later, but there is an argument against formal methods that it requires a PhD to deploy. But a lot of these techniques, such as model checking and abstract interpretation based techniques, they will require a PhD to develop tools based on these, but users don't need PhDs. Okay? Users of theorem proving and engines and proof assistance may require a PhD in most cases, but not all formal methods really require expertise in that particular line of work. And these are various underlying tools that many of these formal methods use in order to complete the verification loop. And let's not go there. So another argument is that formal methods hasn't really scaled, hasn't really achieved much. It's an academic enterprise. And here is a list that I was able to dig up in about 10 or 15 minutes of searching on Google. Some of them are, of course, very well known, and I also have Rockwell Collins up there. And this is really a non-exhaustive, but hopefully representative list of success stories of formal methods. One of my senior colleagues who is at Amazon, who's leading a formal verification effort at Amazon Web Services, he had just posted a question on Facebook asking his colleagues from academia and industry to talk about success stories of industrial development of formal methods. And that was one popular post. So most of this is actually drawn from that post. So I know that, for instance, Rockwell Collins has done a formal verification of a certain microprocessor's partition management, which is used in a wide variety of products, including type 1 cryptographic products. Then Intel has among the largest formal verification teams in their group, and this was, of course, triggered by the infamous Pentium floating point division bug, which cost them $500 million. So what it would take, I mean, sometimes bugs are what it takes for industrial adoption of expensive techniques. Then I'm actually not going to go through all this, but you can see that flight control software, crane networks, Mars, the NASA Mars rover, then of course various units, the arithmetic and logical units across many companies working in the microprocessor industry, all have employed formal verification techniques to ensure reliability. And here I have, in this one line, I particularly want you to notice this one bullet I have here, where there are a bunch of companies. So many of the companies in the microprocessor industry, starting from Apple or an ARM or SoftBank, NVIDIA, IBM, Oracle, have been using formal verification to verify their RTL for years now. So, so this hopefully refutes this argument about where are formal methods used, okay? And I repeat, this is a non-exhaustive list. So this is again another view of what I had on the slide in case people at the back couldn't read. So these, whatever is up here, either is a provider of formal methods technology, or is a user of formal methods technology, or has a formal verification team within the company itself, okay? So, so there is definitely vast industrial adoption of formal methods in the industry already. And here are some of the some specific points that refute some of the common arguments. So I've already mentioned this. Formal methods does not always require a PhD. Many of the techniques are automated or semi-automated. Formal methods does not necessarily require an understanding of the source code to which it's applied, applied, because a lot of these techniques are applicable at the binary level. Then you do not always require the user to provide very precise mathematical formal specifications. Many of these tools will work with some default specifications, such as they will give you guarantees against buffer overflows, memory leaks, race conditions, and so on. And they are scalable, as the previous slides hopefully showed. So I think many of the old challenges that we have been talking about industrial adoption of formal methods, are moot. But there are a couple of challenges that are more new age. So we have complex systems, and we really need to provide guarantees that span the entire stack of the whole system, which can involve guarantees that go across hardware, operating systems, applications, networking, distributed systems, and so on. And just looking at one piece of the whole stack in isolation may not be sufficient. We also need the right abstractions that are needed for both the programmer and the user. And some of these challenges have been discussed and identified in a recent NSF workshop on formal methods for security, which just again goes to illustrate how everyone seems to be recognizing the value of formal methods for security. That's my spiel. Thank you.
That's it.
Hello, I'm Matt Wilding, and I am the manager of the Trusted Systems Group at Rockwell Collins. As already been told to you 5 or 6 times, I have a PhD in computer sciences from the University of Texas at Austin. So our group, Rockwell Collins, is a large company. It makes commercial aviation products and also has a large military business, and with a separate technology center that does research and development. And it has 11 groups in it, and one of them is the Trusted Systems Group, which does a lot of formal methods work, specifically applying it to the broad portfolio of Rockwell Collins products. So what I thought I would do is I would talk about two examples where we've used formal methods in a useful way. One was already mentioned. What we've done is we built a microprocessor that had security built into the microarchitecture of the microprocessor. It's called the AMP7G. And it's kind of cool when you can build your own microprocessors to do things, as we were able to do. And what we did is we took the microarchitecture of the, I'm getting some feedback. Is this, are you able to hear me okay? What we did is we took the microarchitecture of the microprocessor and the microcode that runs in trusted mode, and we modeled all that in a very detailed way. And we're able to prove that, in fact, the information flows in the microprocessor exactly what you'd expect. And that's characterized by this theorem that we proved about the processor. That's come to be known as the GWV correctness theorem. By doing this proof, we were able to come to a claim that the processor does exactly what we said it was supposed to do. And we were able to do our proofs in a way that all the proofs were able to be checked by a mechanical theorem prover. What we were able to do then, of course, it's a wonderful intellectual challenge to prove something about a microprocessor. But really what you want to do is you want to be able to then use that processor in a larger system. And one application of this processor was already mentioned about cryptographic systems. We've also built a high assurance network guards that use that secure processor as well. So we were able to take this theorem and design a high assurance guard, which what it does is it checks to make sure that messages are flowing between networks in a way that's authorized. And by using the formally verified microprocessor, we were able to build a system that we have really high confidence that it's going to do exactly what we say it's going to do. And not only that, but all the evidence that we have to show that the system works the way it's supposed to work is checked by a computer program, which we can provide people that want to evaluate our system and say, hey, you can generate these proofs yourself. Look, here's the theorem that we proved. Go off and generate the proofs yourself using a tool of your own devising, if you like. So that's one example where we've used formal methods in a product development. A second example is a project that we're actually just finishing. It's sponsored by DARPA, and what we've done is we've shown the security aspects of different vehicles. So going back to this earlier example, we're very proud of this theorem. It's key to this larger system where it does network guard work. But there's really sort of no formal connection between the architecture of this larger system and the theorem that we proved about the microprocessor that's sort of the policeman of this architecture. So completely verified, mechanically verified, formal methods proved theorem that's at the heart of the system, but informal, paper-based system architecture that exploits this theorem. What we'd like to do is we'd like to be able to describe system architectures in a more rigorous way as well. And we are doing more and more of that kind of work as well. So in this case, what we're using is architectural description languages to describe in a very precise mathematical way the architecture of a system, and then map that down to a secure platform before we use that microprocessor. In this example, we're using an operating system that's had more formal methods applied to it to show that it's error-free. And what we're doing is then taking this larger system architecture, mapping it down in a very rigorous mathematical way to show that, in fact, the system is correct, at least in some aspects. In this world of security, it's what you end up doing is you can do all the mathematics that you like, but in the end, what you really need to do is you need to hand it off to somebody who can try to find out that you missed something, you did something wrong. Sure enough, the red team that looked at these systems that we did were not able to find any cyber vulnerabilities in the overall system, which, as somebody who worked on the project famously observed, which is really great, because if they had found something, then that would have been mathematics was wrong, and that would have been bad for all of us. One of the questions that we got asked to think about was, what do you think the biggest hurdle is to more and more adoption of these kinds of techniques in these sorts of systems? And I think that the biggest thing that's in our way is the lack of these kinds of industrial scale applications. The more we do of these, the better we get at them, and the more obvious it is to people that want to build these systems that this is the right approach to building complex systems. And if I can take, if the moderator lets me, because I know we're going into question time, but I'd like to take 3 more minutes and say, how do you know, and sort of made me, General Tuhill inspired me to give you this list, because it's a list of 4 things that will help you determine whether or not formal methods is the right thing to be applying in a particular context. It's 4 questions you have to ask yourself. First question is, does anybody really care about the theorem that you're going to prove? In the case of our microprocessor, yeah, we cared a lot. In the case of the cyber resilience of these vehicles, yeah, we care a lot. But you really have to ask yourself, do you really care? The second question is, can you state precisely what property it is that you want to show about the system? Seems like it's a little harder than you might think at first. If you ask people what property they want of their system, and it's an airplane, they might say, well, I don't want it to crash into a mountain. Well, that's not precise enough. You need to tell me precisely what it is you want to have true of it. Can you describe what property you want? Thirdly, do you have a model of the underlying system that is truly the system that you are building? Maybe you're going to reason directly about the code or the hardware design. Do you really believe that when you get done proving your theorem that you say you care about, that you say is an important theorem, that it's really about something that is really the physical thing that you want? That's the third question you have to ask yourself. And the fourth question you have to ask yourself is it the case that you have a tool-supported or somehow plausibly practical way of relating the property to the model of the system underneath? You have to be able to answer all 4 of those questions. If they're all yes, then formal methods is for you. But if the answer to any of those questions is no, then you probably have to think of some other way to do this problem. And that's all I wanted to say. I should let the moderator answer questions.
We have 8 minutes for Q&A, so please keep your questions brief, and we'll try, and the answers brief too. So we'll try to run through as many as we can. Please come to the microphone.
Thank you. I'm Fred Scholl. I'm working on securing agile DevOps pipelines, so I was kind of interested in this. My question is the claim of formal methods that without knowing what the input or abuse cases are, you can determine that the software is indeed secure? Or do you need a clear definition of what the abuse cases are that might attack the particular software that you're analyzing?
Okay, is this on again? Hello? Yes, good. So I think you need a clear, as Matt suggested, what you need is a clear idea of what your security property is. And as long as you know what that is, you can verify it against any use case, all possible inputs, and check that. So there could be something you haven't considered, and indeed this is where formal verification is useful. This thing that you didn't capture in a test case will be covered by the theorem, assuming that your property accurately captures your security requirements.
So just to add to that, if you are unable to come up with a precise description of your security property, you can also go a long way by deploying some static analysis tools which can, for instance, check buffer overflow errors or memory leaks, which are some of the primary reasons for security vulnerabilities. So even if you are unable to come up with a formal characterization of your property, you can still go a long way with formal methods.
Hello, I'm Pascal Meunier at Purdue. I hear what you're saying, that you can prove that your system will behave exactly as you specified. But what I want to hear at the end of that it will do what you specified, but it will not do anything else. And can you enlighten me as to what I need to specify there? Do I need to specify all the things that I don't want to see happen? Or do I just need to specify what I want to see happen?
So it's kind of hard. You know, formal methods is more of a buzzword than it is a precise technology. And I think the right way to think about this is that that you get to describe the property that you want and be able to do a proof about it. But that property is just anything you can write down, anything that you can actually get to a proof about. So if you want to, for example, in the two examples that I showed, take maybe the simpler example of the microprocessor, that it's describing exactly the information flows that are on that processor, and it's exhaustively. So anything that is in violation of those information flows is precluded by that theorem from happening. So that's really kind of more, typically with security properties, you're more interested in what doesn't happen as opposed to what does happen. So hopefully that's responsive to your question. I'll make one other observation. When trying to explain using formal methods to product engineers, one thing that I found has been helpful is you can tell them that you're adding one word to their vocabulary as they write their requirements, and that word is not. Right. A product engineer, a system engineer, typically is not allowed to say this property, not allowed to use the word not in their requirements. And the reason why they can't say the word not is because that requirement becomes untestable. If you say you will not generate the number 12 as an output, well, how do you test that? So a system engineer has been trained from, I'll say from birth, to not write requirements that have that property. When you allow them not to test things, but as opposed to use analysis, you now allow them to add that word to a requirement, and that's a wonderful moment when they realize that they can make that change.
So again, a quick addendum to that. The answer to your question is one might need to specify both classes of properties, and in fact there are phrase names associated with both classes of properties. So safety properties are properties that essentially specify the kinds of behaviors you do not want the system to have. So a system is safe if it does not violate the safety properties. Okay? And there are other classes of properties called liveness properties or progress properties, where you specify that you want something good to eventually happen. And this may not be true often for security properties, but in the broader class of correctness properties, both of these properties play an important role in specifying reliability.
I think we'll have time for 2 quick questions then.
Okay, Chris Clifton, Purdue. One of my favorite examples of formal designs, probably predates several people in the room, was the AT&T 5E switch, which they used formal methods in design of a real industrial scale product. They had one advantage that many companies today don't have. They weren't really worried about someone beating them to market. And my question is, I mean, if your cost of being beat to market is the entire cost of the company, and you can't look at formal methods if they're going to slow you down. To what extent are we able to measure or give examples of the impact on development time of formal methods and show where it saves us, where it speeds things up?
Well, I can give you at least one example. I keep harkening back to that processor example. The day we completed the proofs of it and then ran things through, there was a bunch of government people that then did an evaluation and made sure that we'd done the proofs properly, et cetera. And I was able to very happily report to the person that was responsible for the larger program that we had succeeded. He was surprisingly not happy. And it took me a day or two to figure out why. And the reason why was because we were not the long pole in that process. As soon as we were done, then it became clear that there were other issues in the system. And I would say, this is just broadly speaking, that I haven't seen a delay introduced by doing analysis. There's usually other things that are gating large system developments. I'm only based on a few sample points, but in my heart, I don't think that doing this kind of analysis will be the long pole typically in a big product design.
I would agree with you on the analysis. I would be more concerned about the requirement specification at the level you need in order to do that analysis. What does that cost?
We build requirements for, well, I'm only talking about the industry that I'm in, but we build requirements for all these systems routinely. So that already is the case that we need to incur that cost.
Hi, I'm Shamali Chatterjee from Purdue. So it looks like formal methods have tipped the scale for cases where safety is a major criteria. So what's really tipping the scale for use cases where it's not really safety critical? So what's tipping the scale there in today's world?
So I'll answer that. So I think my security is a concern, and if people can pull off-the-shelf secure by design components, I think that's driving it. So if you can have this security, like if you're developing some autonomous vehicle and you can just pull SEL4 off the shelf, well, there's a win, right? It's security baked in for free.
Yeah, but for cases where safety is not that critical, has the scale been tipped, and what is tipping the scale? What are the factors driving?
Security is always a concern. If someone breaks your system and they steal credit cards, again, the genie is out of the bottle. As I argued, I think the world is more interconnected, and so there are more opportunities for genies to be released.
So I will wrap up with what I take as the single biggest takeaway from each of the panelists. So with respect to Ben's comments, it was enlightening to me that the costs are now, the benefits are beginning to outweigh the cost for formal verification because we're able to stand on the shoulders of giants. Rupsha had a very nice flow of software development and how you can incrementally put in formal methods. So by having the specification be done formally, she also has me worried because because I thought a software engineer graduate from a place like Purdue had a guaranteed job. But she said programs are going to start writing programs and debugging programs. And then Matt had these 4 very fundamental questions that he asked, which will allow us to figure out if formal verification is the right thing to use for a particular system. And here's the question you had all been dying to ask, but nobody asked. What school do you have to graduate from, apart from UT Austin, and still be on this panel? That happens to be the University of Illinois, Urbana-Champaign. Thank you all.